Let's talk about water and hydrogen bonds. In biochemistry, we're going to need to spend a lot of time focusing on the non-covalent interactions that drive biomolecule interactions and folding. So let's remind ourselves about some vocabulary from general chemistry and talking about the difference between covalent bonds and non-covalent bonds. First, a covalent bond, that is a chemical bond that involves the sharing of electrons between atoms to form electron pairs between atoms. So whenever you see a solid line drawn between atoms, that is indicating a covalent bond, and these are pretty strong bonds. We're looking at an energy of about 100 kcals per mole for covalent bonds. And that's in contrast to a non-covalent bond, which does not involve the sharing of electrons between atoms. Instead, it involves dispersed, charge-driven interactions between molecules or within a molecule. So we're thinking things like hydrogen bonds, van der Waals, that kind of thing. Those are our non-covalent bonds. We know we've got a non-covalent bond when we've got a dashed line drawn between atoms, and these bonds are much weaker, on the order of around 1 to 5 kcals per mole. And these non-covalent, reversible, weak bonds are going to be very important to understanding biomolecule structure. The key chemical concept underpinning a lot of this, what we're going to talk about, is electronegativity. You learned about electronegativity in general chemistry, but maybe it's been a minute, so we're just going to quickly refresh. So electronegativity is the tendency for an atom to attract shared electrons when forming a chemical bond. So in general chemistry, we talk a lot about electronegativity trends, where if we look at the periodic table, we see that we increase in electronegativity as we move from left to right, and we also increase in electronegativity as we go from the bottom to the top of the periodic table. And in our, organic chemist or biochemist periodic table, really, I just need you to think about oxygen and nitrogen being more electronegative than carbon and hydrogen. So hydrogen bonds. Hydrogen bonds form between atoms with a partial positive and a partial negative charge, where water is the classic example. Let's see how electronegativity and dipoles play into this. So when we have hydrogen and oxygen covalently bound, oxygen is more electronegative than hydrogen, so that means oxygen will attract those shared electrons more towards itself, and hydrogen doesn't quite get its fair share of electrons. So that means these electrons are unequally shared, which creates what's called a dipole. So if we were to make a plot of where the electron cloud is in 2D or 3D space, we would see that oxygen is hogging most of those electrons that come from their covalent bond. So because oxygen has slightly more electrons than it should, it gets a partial negative charge, and hydrogen has slightly fewer electrons than it should, so it gets a partial positive charge. So now when we think about water, again, here we have our hydrogen bound to our oxygen, covalently bound. That hydrogen is going to take on a partial positive charge. The oxygen will take on a partial negative. By the way, this symbol here, that's a lowercase delta, and it means partial negative in this example. So then that partial negative charge on the oxygen can interact with a partial positive charge from a hydrogen on a neighboring water molecule. So this is why this is called an intermolecular interaction. Here's one water molecule, here's another water molecule, and inter means between, so between two molecules, intermolecular. This is also a non-covalent interaction. This oxygen is not covalently bound to this hydrogen. Instead, they're forming a non-covalent, weak, transient interaction that is the hydrogen bond. So because hydrogen bonds are fairly weak, what that means is that they're going to be pretty dynamic, forming and breaking all the time. So water, thinking about it as a solute, we can imagine all these water molecules that form a dynamic network of hydrogen bonds that are constantly forming and breaking. And because of that, water is great at solubilizing polar molecules due to favorable hydrogen bonding interactions. So what else? Hydrogen bonds. Generally, it's going to be a nitrogen or an oxygen that's covalently bound to a hydrogen, and this is going to be a polarized bond, or it's going to have a dipole moment where this atom here, so the nitrogen or oxygen, will take on a partial negative charge, and then the hydrogen will take on a partial positive. So this partial positive, this hydrogen right here, is called the hydrogen bond donor, and then what it's interacting with is called the hydrogen bond acceptor. So that's going to be, again, a nitrogen or oxygen with a partial negative charge. So here's one example where this oxygen atom here is going to have a partial negative charge, and then this hydrogen is going to have a partial positive because it's in a polarized bond with this nitrogen. Water can come in and compete for that hydrogen bonding interaction. So right now they're hydrogen bonding, but water can come in and make alternative hydrogen bonds. So here's a water molecule interacting with that oxygen. Here's another water molecule interacting with that hydrogen. So molecules that form hydrogen bonds can be solubilized in water, and that's going to get us to our big key concept of solubility and favorable interactions in a hydrophilic environment. This is what makes a molecule hydrophilic, is its ability to hydrogen bond with water. Water can also form ion dipole interactions. So you know that you can dissolve some salt in a glass of water. So solid salt, crystalline salt, has this structure right here, with your sodium ions forming ionic bonds with your chloride ions. But then when you dissolve it in salt, water can surround those ions to make an ion dipole interaction. So think about what this looks like. Here's our ionic interaction between our chloride and our sodium ion. Another word for an ionic interaction is a charge-charge interaction, means the same thing. And when it's solubilized in water, we're going to get an ion-dipole interaction, where here's our water that's got a dipole in it. And so this partial negative on your oxygen can interact with the full positive charge on the sodium. So again, this is our ion-dipole interaction. That's why salts favorably dissolve in water. We can describe the strength of these interactions, mathematically. So if you think back to physics, you might recall Coulomb's law that describes the strength of electrostatic interactions. So what do I mean when I say electrostatic? So if we just break this word down, electrostatic is sort of like a fixed charge interaction. So under that umbrella, I'm counting hydrogen bonds. Another word for those are dipole-dipole interactions, means the same thing. I'm counting ionic interactions, also called charge-charge interactions or salt bridges. And I'm counting ion-dipole interactions, so for example, between water and salt. This is Coulomb's law, where on one side we have energy, and remember that a negative energy is more favorable. We have a constant, we have our two charges, so that could be like a +1 for a sodium, and then it could be maybe a -1 for a chloride, or it could be +2 for a calcium and -1 for a chloride, etc. And then on the bottom, we have R, which is the distance between the two interacting atoms, and then we have D, which is the dielectric constant, which we'll talk about more. But what you see here is that you could plug into this equation the charge of the two interacting atoms, their distance, the dielectric constant, which again we'll talk about, and calculate the energy, so predict the strength of that interaction, which is a really powerful tool. So what is the dielectric constant? So dielectric constant, the symbol is a capital D, and it describes the ability of a substance to insulate charges. What do I mean by that? So let's say I have a charge and I try to pass it through water. Water is a pretty good charge insulator. It's not going to pass through very well. So it has a high dielectric constant because the charge is instead interacting with the water molecules. Benzene, which is a nonpolar molecule, passes charges really well. So the dielectric constant is small, like 2. If we had a complete vacuum, the dielectric constant for that is 1. So prove it to yourself. Here's a practice problem you can work on your own. Consider a charge-charge or ionic salt bridge interaction formed between the amino acids glutamate and lysine. So here's the structures down here. We've got lysine. The side chain for lysine is positively charged. We've got glutamate, also called glutamic acid. The side chain for that is negatively charged, so we have a formal positive charge interacting with a formal negative charge. Will this bond, this non-covalent ionic interaction, be stronger in an aqueous environment like water or in a hydrophobic environment? So use Coulomb's law, prove that to yourself, come up with the answer to this question.